Hi, I'm Amir Hossein Mirzabozorg. In this video, I'm going to talk about the XFEM technique in Abaqus. You can use extended finite element method for simulating the crack initiation and crack propagation in Abaqus CAE. In this video, I will talk about the XFEM limitation and XFEM capabilities in Abaqus CAE. I'm going to demonstrate some of the examples that I have solved by using extended finite element in Abaqus CAE. Here I want to show you some of the models that I have solved them by using XFEM technique in Abaqus CAE. I open this CAE file. This is a 2D model. You can see that this part is 2D and there is a hole in the plate and it causes a stress concentration here, and we apply a tensile displacement control load on the top of this part, and the first fracture mode will occur. I have defined this material for the part. I have defined elastic property and max PS damage. In the Abaqus CAE, the XFEM technique can be solved by using two different methods. The first method, that is the traditional method, is based on the VCCT technique. I mean the virtual crack closure technique, and the other one is based on the CZM technique. I mean the cohesive zone method. And the first one is only applicable for brittle materials, and the other one is applicable for both of the brittle and ductile materials. And in this model, I have used the second method. If you want to use the first method, you must define the XFEM properties in the interaction module. But if you want to use the second method, you must define the damage behavior in the property module and from the damage for traction separation loss. You can see that there are 6 behaviors in the property module for defining the criteria of initiation of the crack. 3 behaviors are based on stress, I mean quad S, max S, and max PS. And 3 methods are based on strain, I mean quad E, max E, and max PE. And for example, the formulation of quad E and quad S are similar. In one of them, the strain is used, and in the other one, stress is used. Here I have used max PS criteria, and this criteria means that if the principal stress in the tip of the crack reaches this amount, the crack propagation will initiate. But the path of its propagation depends on this behavior, damage evolution, that I have defined it too because I want the propagation of the crack. And there are many settings here. The damage evolution can be energy based or displacement based, and softening can be linear, exponential, or tabular, and exponential and linear decay are very famous. And you can choose the mixed mode behavior, mode independent behavior, power law behavior, and decay are famous. And here I have used power law method. And here I have defined a brittle material because I have not defined the plastic region here. So we have only two regions, the elastic region and the damage region, that is solved by using XFEM technique. You can see that there is no initial crack in this structure, and XFEM technique can only be used with Abaqus standard solver. For static problems, you can use a static general step or dynamic implicit step, and for dynamic problems, you can use dynamic implicit step. And when you want to use the XFEM technique, you must define the enrichment zone. The enrichment zone is a domain that the crack can propagate and initiate in it. By using partitioning tools, I have separated this region because based on my physical and engineering sense, the crack will initiate from this region and it will propagate in this region because due to the loading, the first fracture mode, that is the normal mode, will initiate. I have defined the loading. I have fixed this edge and I have defined displacement control loading here, and I have defined coupling constraint for this edge, and this is the mesh of my model. For having an exact solution, I have created dense mesh here because the accuracy of the solution depends on the size of elements. And I want to show you the results. This is the result. You can see the stress concentration in the increment 1. And you can see that 3 cracks are initiated. I want to use a status XFEM that shows the line of crack. you can see that just one of the 3 cracks has propagated, and you can see that finally we have encountered too many atoms error because of the instability of our structure. And I have solved this problem by using smaller elements. This is the second mesh, and you can see that the size of the elements are smaller than the size of elements in the first model. And I want to show you the results. The results files need a huge space that my computer can hardly load them. I want to show you the size of the ODB file of the second model. It's more than 4 gigabytes. And its file is so huge. And I want to show you the results that are very strange. You can see that more than 3 cracks are initiated. And some of them are propagating. I think that because of having small elements in the model, the accuracy of the results has decreased due to the round of errors. Because I have not used the double precision simulation. I have used single precision, but I think I must use double precision or full precision. But it will increases the time of simulation and the runtime. And notice that if the size of the elements are very smaller relative to the model, you must use the full precision for your simulation for minimizing the round of errors. Now I want to show you another model I have simulated a CT specimen of aluminium, and these edges are created for separating this domain because the crack propagates in this domain, and I have created smaller elements here. And you can see that I have defined elastic behavior, plastic behavior, and max PS damage and damage evolution, because aluminium is a ductile material and it has plastic domain, and it's very important for our simulation. And I want to show you the mesh of the model and now I want to show you the results. The difference of model 1 and model 2 is the amount of fracture energy. In the first model, I have used this amount for the fracture energy, and in the second model, I have used this amount for the fracture energy. You can see that if I multiply this amount by 1000, it will be equal to this amount. Now I want to compare the results. You can see that the difference is only due to the amount of fracture energy, and its amount highly influences the results, and you must use an exact amount for it. You can contact us by using Telegram or WhatsApp or using email. These are our paid services: one-on-one tutoring on Skype, WhatsApp, and making special videos to your order and answering your questions. High-quality simulations for thesis, exercises, and industrial projects by using Abaqus. all of our services are paid services. We can adapt our services according to your conditions and your needs. The cost of services depends on the subject of your project and its complexity. And it means that our costs are not predefined. And it depends on the complexity of the project. The cost of service must be paid by PayPal. This is the only way for transferring money for us. Thank you so much for your attention and concentration. Good luck.